This chapter begins two-dimensional kinematics. For Physics AB, Honors Physics AB, and AP Physics C, this begins to cover Chapter 3. Now, to some extent, we've already done a little bit of Chapter 3. I did a little bit of Chapter 3 early on prior to looking at one-dimensional motion by taking a look at the basics of vectors. We're going to see the basics of vectors appear here in this chapter once again. There are two important types of motion to examine here in Chapter 3, covering two-dimensional kinematics. Before we get to those important types of motion, however, the first thing that I have to go through is notation. The notation that we use to describe position, velocity, and acceleration when talking about two-dimensional cases. Okay, so let's say that we begin by having two-dimensional space. Like so, here's the x-axis, and here's the y-axis. And then when we start the clock, let's say we have an object that has some position with respect to the origin. Like so. Okay, now right here is the initial position vector associated with that object. We always use the letter R to describe position when talking about the two-dimensional case. So then therefore we label this as the initial position R0. Like so. Okay, now I'm not going to draw the components of this vector here on the board, because if I did, then the board would get a little bit crowded, the diagram that is. But instead, off to the side, let me go ahead and write the initial position vector here in component form. Right here is the component of the initial position along the x-axis. As it was back in Chapter 2, this is x0. Right here is the component along the y-axis. This right here, as it was back in Chapter 2, is labeled as y0. So then therefore, in component form, the initial position vector R0 is written in the following way. Like so. And notice the return here of the I hat and j hat notation that we saw when going through the basics of vector mathematics at the beginning of Chapter 3. Okay, now some time interval goes by, and let's say that the object ends up over here somewhere else in space. Therefore, with respect to the origin, right here is the final position vector R. The final position vector R can be also written in component form in the following way. So right here along the x-axis is the final position X. Right here along the y-axis is the final position Y. Okay, over the time interval, the object underwent a change in position. Using the tail-to-tip method of vector addition, the change in position vector delta R is drawn in the following way. Notice that I drew it as initial plus change is equal to final. So using the tail-to-tip method, the initial plus the change is equal to the final. Therefore, the change in position vector delta R is equal to the final value minus the initial value, like so. Okay? Okay, that describes position. Now let's just move on to velocity. Okay, first of all, for velocity, we begin with the average velocity. Okay, the average velocity is still written as v bar, like so for average, but now we do include the vector sign, like so. And then by definition, the average velocity is the change in position divided by the change in time, like so. If we then take the time interval and make it infinitesimally small, then we end up with the instantaneous velocity. This then gives us our first derivative. So the instantaneous velocity v is a limit as time approaches 0 of change in position with respect to time. This is how we saw it in Physics AB. However, in Honors Physics and in AP Physics, we would see this as the derivative of position with respect to time. Okay, now here's what velocity looks like in component form. What we're doing is we're taking the derivative with respect to time of the position vector in component form, which is here on the top board. Like so. And now when we differentiate this quantity, the I hat and the j hat are constants. They always have a magnitude of 1, and they always point in specific directions. So then therefore, when we do take the derivative of the quantity here in parentheses, we are just differentiating the position in the x direction with respect to time, and then we're taking the derivative of the position in the y direction with respect to time. That then looks like this. so. And then this right here is the component of the velocity vector in the x direction. This guy here is labeled as v sub x, like so. And then this right here is the description of the component of the velocity in the y direction. This right here is just written as v sub y, like so. So in component form, this is what the instantaneous velocity vector looks like. For those of you enrolled in physics AB, going from this qualitative description here to this description here is fine as it is. So as the object on the top board is moving around in two-dimensional space, bam, at some moment in time, it has an instantaneous velocity vector. Let's just say that instantaneous velocity vector looks, say, something like this. So at some moment in time, let's say the velocity vector v looks like this, and then in component form, right here is the x component, v sub x, and then right here is the y component, v sub y, like so. Okay, keep in mind that as I go through this process, you are not seeing anything new here. This is all just position, velocity, and then in just a few moments, acceleration, but now all just dressed up in terms of its full I hat and j hat notation. Okay, now we do this process of taking a derivative one more time to go from velocity to acceleration. Okay, so first of all, we have the average acceleration, which is written as a bar and then the vector sign above. This is equal to change in velocity v with respect to time. Now, a little bit of notation here in the numerator of the expression. The change in velocity delta v, that's equal to the final velocity minus the initial velocity. In component form, the initial velocity vector v naught would be much written like this, but just with an extra naught symbol, like so. So the initial velocity vector would be the initial velocity in the x direction, that's written like so. And then here's the initial velocity in the y direction. That's written like so. Okay, now to go from this description here of average acceleration to instantaneous acceleration, we then take a limit as the time interval shrinks to 0. Okay, so instantaneous acceleration is the limit as time approaches 0 of change in velocity with respect to time. Okay, once again, those of you enrolled in Physics AB, you would qualitatively just see it like this. However, for those of you in honors and in AP, we now have another derivative. Derivative of velocity with respect to time. So in component form then, in order to come up with the components of the acceleration vector, what we're then differentiating is this quantity here with respect to time. Okay, once again, the I hat and j hat unit vectors are constants, so they just get dragged along in this process of taking derivatives. So in the first term here, we're differentiating the velocity in the x direction with respect to time. That looks like this. And in the second term, we're differentiating the velocity in the y direction with respect to time. That then looks like this. And then this right here is the component of the acceleration vector in the x direction. This is labeled as a sub x. This right here is the component of the acceleration vector in the y direction. This is labeled as a sub y. So in component form, the acceleration vector is drawn like this. For those of you enrolled in Physics AB, going from this qualitative description right here of the derivative to this description right here, that's perfectly fine. So as the object is moving around in two-dimensional space on the top board, boom, at some instant in time it has an acceleration vector. That acceleration vector would be drawn out like so. So as it moves around on the top board, at some moment, let's just say generically the acceleration vector looks like this, and it has components. Right here is the component in the x direction, a sub x. Right here is the component in the y direction, a sub y, and then in component form, we then write out the vector in the following way. So basically, to boil it down, we have, once again, position, velocity, and acceleration, now just all dressed up in its full vector notation with I hat and j hat describing the components. Now that's for a two-dimensional case. What about a three-dimensional case? For a three-dimensional case, in addition to the XY plane, you would have the third dimension, the Z direction, perpendicular to the 2 like so, perpendicular to the board. What that would then mean is that all of these vectors that I've been drawing out here for the last 10 minutes or so would have a third term. There would be a Z component associated with each of these vectors, and the unit vector associated with the third dimension is k hat. So I hat, j hat, and k hat are the unit vectors that are used for x, y, z to describe three-dimensional space. However, here in chapter 3, for the remainder of the chapter, we're only going to be looking at two-dimensional cases, two very important types of motion that occur near the surface of the Earth. We'll get to those in the next series of lectures.